So this is our fourth lecture on psychrometrics. We've been in psychrometrics for 3 lectures. What do we need to do? We still need to solve some application problems. And then last, I'd like to introduce a psychrometric chart. A man named Carrier basically came up with the first psychrometric chart probably around 100 years ago. And it's been adapted and improved, and it's really useful for heating, ventilation, air conditioning calculations. We can solve a problem by hand, and then we can, if we have time, solve it again with using a psychrometric chart. So we have moist air at 25 C, given atmospheric pressure 101.3 kilopascal, 75% relative humidity. It flows over a cooling coil. Will the coil surfaces be hot or cold if it's called the cooling coil? Really cold. It's going to cool the air flowing over it. It's just the way you talk about it. Okay, and it has a dry air flow rate of 2.5 kilograms per second. So we organize the information. The mass flow rate of dry air, 2.5 kilograms. A lot of times I'll put dry air kilograms per second. It's not moist air kilograms per second. It's dry air. All right. Is the moist air mass flow rate going to be a little bit above that or a little bit below that or precisely the same? You're going to add vapor to it. So it'll be a little bit above it, won't it? The total mass flow rate of the moist air is going to be a little higher because of the vapor added to it. Okay. The air leaves at 12 C, 100 kilopascal, 95% relative humidity. Determine the volumetric flow rate of the air entering the coil. How am I going to determine the volumetric flow rate of air entering the coil? I need to pause. I need to walk around and just see if you can come up with that equation. All right. Well, I promise I'll give you as much time as I can, but I can't give you a whole lot of time. Sorry. Got to cover a lot of material. So anyway, you have that the volumetric flow rate times the mass density is the mass flow rate, or the volumetric flow rate divided by the specific volume is the mass flow rate. This time we're given the mass flow rate, so the volumetric flow rate is equal to the mass flow rate times the specific volume. You are absolutely correct. That's the right equation to use. It's just that I have that this is the dry air mass flow rate. I need to multiply by the particular volume, specific volume. It's the specific volume of the dry air. It's how many meters cubed of the moist air are occupied by per kilogram of dry air. So how do I calculate that? This is the R bar T divided by some P molar mass. Okay. Which pressure are we talking about? The total or the dry air or the vapor pressure? It is the dry air, partial pressure of the dry air. And this molar mass is of the mixture, the moist air mixture, or the dry air or the vapor? Dry air. Yeah, don't get tripped up on those. And so then you would calculate it. And if you calculated it, you get about 130 meters cubed per minute. Okay. Will that be... It's coming into a cooling coil, and that's our volumetric flow rate coming in, AV coming in. The volumetric flow rate going out is very close to the volumetric flow rate coming in, and if you're working in the industry and you need to do a back-of-the-envelope calculation, the standard assumptions are so close you neglect it, but it's going to be a little colder going out. That means the air is probably a little denser. And so what do you think that the volumetric flow rate going out might be a smidgen greater than or a little less than what it came in at? Less. That's right. It doesn't need as much volume to carry that air because the air is more dense because it's colder. Right? Perfect. Good. Okay. Now let's press forward. What is the condensate flow rate leaving the coil? So you have a really cold coil, and you pick up some condensate right here, and I'll call that the mass flow rate of the liquid coming out. How am I going to get that? How am I going to calculate the mass flow rate of the condensate coming off of that cooling coil? You're going to do a water balance, a mass balance on the water only. And when you do a mass balance on the water only, right here, we have that the mass flow rate of the vapor coming in equal to the mass flow rate of the liquid going out, liquid water going out, plus the mass flow rate of the vapor going out with the air stream going out. Is that a good water balance? And then we see, how do I calculate that mass flow rate of the vapor coming in? I'll use the mass flow rate of the dry air, and I'll multiply by humidity ratio coming in. And then I have the mass flow rate of the liquid plus the humidity ratio going out times the mass flow rate of the dry air. Are these two dry air flow rates the same? Yeah, that's why engineers like the humidity ratio. And so the mass flow rate of the liquid would be the higher inlet humidity ratio minus the lower exit. If the humidity ratio doesn't change, if omega 1 is equal to omega 2, guess what? You have no liquid. But you then multiply by the mass flow rate, and there you go. We know the mass flow rate of the dry air. How do I get omega 1? 0.622 PV over P minus, so omega 1, it would be 0.622 PV1 divided by P minus PV1. And the same thing for it. Okay, if I do that, I'll calculate 1 kilogram a minute. So 1 kilogram, you're thinking about one decent sized liter water bottle. That's how much condensate per minute coming off. All right, what about the rate of heat transfer from the air to the coil? So the coil is accepting some heat transfer from the air. The coil is cold, the air is warm, it's transferred from the air to the coil. A lot of times we might draw it like this. What is that Q dot to the coil? What is the Q dot out of the air? How do I calculate the Q dot out of the air? Do it two components. One component would be how much to cool the dry air. Well, three components. Mass flow rate of the dry air times, let me do the enthalpy exit minus, inlet minus exit will give the rate of the dry air because I want a positive Q dot out. And then we're going to do the mass flow rate of the vapor that exits, and then we'll do the mass flow rate of the liquid. That gives me the right three components. Some vapor is just cooled, so it goes out H1G minus H2G. This is of the vapor. And then if it's liquid, it's H1G coming in, but what is it going out? F at 2 or 2F. There's to me, nothing special about HG1 or H1G. So sorry about that. H2F. Makes sense? And we did some calculations, and often if you have a large M dot of the liquid, this component, that piece of the three pieces is large. Takes a lot of cooling to condense water vapor. So you compute to 75.5 kilowatts. Ready to move forward? You can solve that problem using a psychrometric chart. Hopefully with time we will. Well, where's the psychrometric chart in our textbook? Well, you just hunt back in these figures. And can you see anything that says something close to the psychrometric chart? Yeah, right at the very bottom. So we have the psychrometric chart in SI, or don't call it English, United States Customary System of Units. Nobody in England talks in BTUs anymore, degrees F and all that. Just leave the English alone. United States Customary System of Units. There you go. So this is the chart. I'm going to pause and pass out a chart for you.